size of a small house.
Stand by for GPS coordinates of our primary objective, the large house-sized rock. Over. What we're going to be doing here is we're going to be measuring the size of this boulder and also sampling pieces, chunks, slivers off it all around, trying to see how much is being eaten by lichen and other forms of microscopic life. There are green stains, vermilion-colored lichen, even mossy material in here, as you can see. So we'll be trying to figure out how many fractures there are, because microbes like to live in those fractures. And then we'll have a pretty good idea of how many kilograms of life are in this rock.
It's not clear that this rock was sent here by the impact. It may have been. We're trying to determine that.
This stuff seems to have been very much molten, almost like a lava, a frothy lava. There was a lot of gas that came out of this, carbon dioxide probably. It's obviously impact related. It is a pudding of fragments held together by a froth of molten rock, so I would tend to believe it was kicked out of the crater by the impact.
Next, the crew is supposed to find out how big the rock is.
Robert Curley has the tape measure out.
This rock is 25 feet long. We'll measure the width and the height as well. If we know the size of the rock, we can calculate the mass of the rock, and that would give us an idea of the force that had to eject it to fly it this far, if indeed it was ejected by the impact. Now we're going to try to get some idea of how tall it is. Right here.
Using a simple system of geometry, measuring various triangles and sighting up to the top of the rock by eye, they come up with a good estimate for the height.
That would therefore mean the rock is about 21 feet high.
Based on the size of this and other ejecta blocks, scientists calculate the meteor which smashed into Devon Island must have unleashed a force that was 50,000 times more powerful than the nuclear bomb dropped on Hiroshima.
Other things. Who wants to cook tonight?
You just have to think about it. You're basically shopping for a family of 6. But now, on an actual Mars mission, of course, you'd want to stock up for a year and a half.
Here in the habitat, at least while Zubrin has been commander, crew members are taking turns cooking each night. While the ingredients they have to work with mostly come from cans, on a real Mars mission, most things would be dehydrated to save weight. As for why they don't just eat space food, the answer is simple. It's a nice change from rushing around in spacesuits. Perhaps astronauts on Mars will feel the same way.
Why are the forks on this side? Is this a Martian custom?
You know, in America, people hold their forks in the right hand.
Really?
The crew comes together best at dinner time. That's when we all can sit down and relax. We're usually pretty beat, especially those who've been out on EVA. But it's a fun moment, and there's a lot of cracking jokes.
The inner planet goes on the inner orbit, the outer planet goes on the outer orbit, and between the two there's an ellipse defining the home and transfer, the minimum energy trajectory between the two worlds.
So we have a good time at dinner, and the food's excellent because we really put our heart into it. We try to outdo the other cooks, and the food, for that reason, has been superb.
So far, so good. Looks safety.
After dinner, of course, comes washing dishes. And that means tapping into a resource that will be precious on a Mars mission.
Water. Water is the staff of life. And it's the key issue in a human Mars mission. On Mars, it's the key substance that we're looking for as part of our search for life. It is, in fact, the central issue that will determine whether a mission will occur at all. A human Mars mission will only be possible if we can keep water consumption tightly constrained and recycle the water that we use. So we're going to get a fill soon, so on like July 19th, 9 a.m. We do a water refill here about once a day. Our tank has a maximum capacity of 35 gallons. It's coming in.
Well, we were. Stop. We're not recycling water here as you would on a Mars mission. We don't have the equipment for that.
How are we doing with the water, Robert?
Well, we got a ways to go.
All right.
What we are doing is we're counting the amount of water that we're using, because after propellant, water is by far the largest consumable used on the mission. I have to emphasize that the amount of water a crew uses is the most important logistics variable of a human Mars mission. It determines the mass of the mission, it determines the cost of the mission, and therefore it determines the political possibility of the mission. You use much more water than you use food or oxygen. Not so much to drink, that's comparable to the amount of food that you eat.
We're learning well.
But to wash with. Wash pans and your hands and your face and clothes and showers. There's no way a Mars mission, even with the best recycling gear, could put up with water use on the scale that people are accustomed to doing it in modern society.
After every activity that involves using water, crew members climb up to the storage tank and measure how much less there is than when they started. The hope is to understand how much water they really need to get by.
Now, measuring the amount of water that we're using determines how much water needs to be either supplied or recycled a day. Additional questions revolve around what kind of recycling system. And in order to understand that, we are doing chemical measurements of the quality of this water and of the quality of the gray water that we drain from the hab. So, in looking at what you have to do to change that water back into this kind of water, you learn about what kind of recycling system you're going to need. The amount of water tells you the size of the recycling system. The chemistry tells you the kind of recycling system. And on the basis of that, we hope to develop a water recycler that we'll be able to implement here next year.
Okay, thanks, Brett. Over.
It's day 17 in the Mars simulation, and a new crew member arrives with some unusual American military technology.
My name is Lieutenant Colonel John Blitch.
Treat it like American football, and you're running for the end zone.
I'm a program manager for the Tactical Mobile Robotics Program at the Defense Advanced Research Projects Agency.
And remember not to grab the camera as the handle.
The area of portable robotics has a wide range of application, and I think there's a lot of commonality between military applications and this particular endeavor.
On ladder coming down.
It's got a turret on it.
On a human mission to Mars, I think we've got some very daunting tasks. You can't go out every day. There are going to be situations where dust storms are covering the entire surface. A human-only mission is destined to fail. So the notion here isn't just to reduce risk to those humans. It's to reduce the risk of failure on the mission.
Well, these are all male robots because they're tethered and they have no onboard intelligence.
Okay.
And conversely, I think that unmanned missions aren't adaptive, and there are unanticipated things that go wrong.
This particular system has a microphone, 2 speakers.
Without robots, we can't do it. Without people, we can't do it. It's the combination that will enable the entire mission to succeed. We're going to be very challenged.
It looks like this one. Is this the one with the variable focus? It looks like
yes, it is. Yeah.
There are a wide variety of tasks that humans simply can't do.
When we're in those spacesuits, we're not going to be able to just lay on our back and look up underneath.
Inspecting this habitat, for example, there's a lot of confined spaces here, and we do not want to get into the situation where we have to disassemble half of the habitat just to replace one little wire.
Okay, so these are actually the wooden structures we'd actually like to take a look at. Yeah.
It's one thing to use robots for inspection and maintenance, but can they help astronauts explore where it's too dangerous for people?
Okay, so here's a plan.
The mission today is to go to the rim of a steep canyon and to attempt to explore it from the canyon rim using telerobots.
We're going to lower this platform down a steep slope that was probably too steep for a human EVA team.
It's a long drive out to the canyon, and on Mars,